We have seen that by substituting the resistive load of a common source amplifier by an active load, that is a MOS transistor operating in saturation, we can decouple the supply voltage from the gain. That is, we can realize a large gain using incremental resistance that is very large, while keeping the voltage drop across the device to be small. Okay. There are some more details to be worked out as to how to ensure that the transistors remain in saturation region, but we'll discuss a few more variants of the circuit before going there. The circuit that we looked at was a PMOS common source amplifier with NMOS active load. So we have the PMOS transistor whose gate is biased at some VGP, and an NMOS transistor whose gate is biased at VGN. The output is taken here. So this is the load and this is the amplifier. In this case, this is MP and MN, and to the gate of the PMOS transistor we applied the small signal input Vi. The output is at a certain bias voltage VO bias. We assume that both transistors are in saturation region and there will be an incremental output VO. We know that VO would be minus GMP, which is the GM of the PMOS transistor, divided by GDSP plus GDSN times Vi. Okay. Now it's pretty obvious, I won't go into the details of this, that exactly the same thing can be done with an NMOS common source amplifier. We started with the PMOS common source amplifier, but we can start with an NMOS common source amplifier with PMOS active load. So a conventional NMOS common source amplifier would have an NMOS transistor operating in saturation region, loaded by a resistor RL. The gate is biased at VGP. As with the PMOS common source amplifier, if we go on increasing RL to increase the gain, we have to increase the supply voltage VDD as well. To avoid that, we can replace RL by a PMOS active load and we take the output here. You can see that the circuit looks exactly the same, except that in this case the input is applied to the NMOS transistor and the output is at exactly the same place. Again, we assume that both transistors are in saturation region at the operating point. Okay. So again, we can write the expression for VO, and it's pretty obvious that in this case we have the transconductance or GM of the NMOS transistor divided by GDSN plus GDSP times Vi. Okay. So the two circuits are exactly the same. If you look at it, we have an NMOS transistor at the bottom and PMOS transistor at the top, the same here. The only difference is in which transistor the input is applied to. Okay. We already know that if you have a circuit with a certain polarity of transistors, you can flip them, that is, turn all the NMOS into PMOS and PMOS into NMOS while not changing the behavior of the circuit. We can convert from one type to another. We could have got the second circuit from the first circuit by doing exactly the same. Okay. If you look at the circuits for a little while, new variant becomes immediately obvious. Here we are applying the input to the PMOS transistor Here we are applying it to the NMOS transistor, and the circuits are the same. Why not apply the input to both? So we could also do this. And we apply the inputs to both of them. There will be an incremental output. What is the value going to be? The answer is pretty obvious, but I'll anyway work it out and show. I'll draw the incremental equivalent, in which case we have only the increments. The incremental equivalent of the PMOS transistor is like this, where this is GM times VGS and this is VGS. This is ground. And the incremental equivalent of the NMOS transistor is like this. This is VGS. Let me distinguish P and N by adding another subscript. VGS P, VGS N. This is GMN times VGS N. Okay. And the same incremental input is applied to both of them, meaning in the incremental picture these two are at the same voltage. And we also have the output conductances of the two transistors, GDS-P and GDS-N. It's very clear that the incremental output Vout is going to be minus GMN plus GMP divided by GDSN plus GDSP times Vi. So the gain is larger than, the gain in this case is larger than what either of these two amplifiers provide, and in fact it's equal to the sum of the two gains. Okay, you get GMP when you apply the input to the PMOS transistor, you get GMN when you apply input only to the NMOS transistor. If you apply it to both, we will have GMP plus GMN. So that's also an advantage, and sometimes this structure, the one where the input is applied to both of them, is used for obtaining a higher gain. Okay. Now, in this particular case, we can choose VGP and VGN to be anything we want really, okay, and that can be done. But there is a particular variant that is used quite often. That is where we make VGP and VGN to be exactly the same. Now remember, the incremental input applied to the gate of the PMOS and gate of NMOS is the same, but the bias voltages are different here. And we cannot make the bias voltages also the same, in which case the gate of the PMOS and gate of NMOS transistors are the same for both incremental and bias. They are simply tied together. Okay. So that's a particular variant of this circuit, and it happens to also be a very popular circuit used in various contexts. This basically says that VGP equals VGN. Okay, and I'll simply show this as a large signal input Vi. Okay, earlier I showed it as bias voltage plus some small signal input. I'll just call this large signal input Vi and a large signal output Vout. Okay, some of you may already recognize this circuit. This is what is known as a CMOS inverter, and most likely you would be familiar with this in the context of digital gates. But basically a CMOS inverter is a common source amplifier, or some variant of it, a common source amplifier with an active load, in which the input is applied to both N and P sides. Okay.